Hello, everybody. We'll wait a minute or two for everybody joining, and then we'll start with the webinars. Okay, so I'm going to start doing an introduction. So hello and welcome to the Institute for Molecular Science and Engineering's webinar, Micro and Macro Fda Spectroscopy and Imaging for Heritage Science. The event is also supported by the Science and Engineering Research for Cultural Heritage Network of Excellence. I'm Dr. Salvador Eslava, a senior lecturer in the Department of Chemical Engineering here at Imperial. All the webinars in this series address science and engineering research for cultural heritage. We'll be putting some helpful links in the chat function, including links to the Eventbrite page, the YouTube channel, the blog, the Never Lick the Spoon podcast, all of our previous briefing papers, and the link to the registration to our newsletter. Before we start, please make sure that your microphone and video are switched off. And remember that if you wish to ask a question, please do many. Please put them in the questions and answers function of Zoom at any time during the webinar. And at the end, I will read the questions. Don't put the questions in the chat function. If you have any technical difficulties, please message IMSE Imperial privately and we will help you. I will first introduce the speakers of today. We have Dr. Francesca Rosi and Professor Sergey Kasarian. The first one will be Francesca. Dr. Francesca Rosi is a senior researcher at the Institute of Chemical Science and Technologies of the Italian National Research Council. In 2005, she was awarded a Ph.D. in chemistry at the University of Perugia for the dissertation titled Spectroscopic Studies for the Conservation of Mural Paintings. She's an expert on advanced spectroscopic methods for the study of cultural heritage materials with a particular focus on non-invasive portable systems. She has participated in the activities of the MOLAB platform, the European Infrastructure for Heritage Science, and the European IPERION-HS project. She has also participated in the international projects Futurama, HeroMat, IT@CHA, Charisma, and ERIHS. She's an author of about 90 papers dealing with the development of analytical strategies for heritage science, non-invasive in situ studies, and microscale investigation of cultural heritage materials. The second speaker will be Professor Sergey Kasarian. He's a professor of physical chemistry in the Department of Chemical Engineering at Imperial. His scientific research began in Armenia using infrared spectroscopy to study matrix isolation of weak complexes of CO2 with metal atoms. He further developed this technique during his PhD in the 80s in Moscow at the Academy of Sciences. He worked as a research fellow at the University of Nottingham in the UK and as a research scientist at Georgia Institute of Technology in the US. He joined Imperial College London in 1998 and was promoted to professor in 2006. He leads the research group Vibrational Spectroscopy and Chemical Imaging. Professor Kasarian is a fellow of the Royal Society of Chemistry and the Society for Applied Spectroscopy. He's the editor-in-chief of Applied Spectroscopy and has published nearly 300 articles in reviews in leading scientific journals and cited more than 16,000 times. His research encompasses analysis of materials of cultural heritage collections. He has also collaborated with different museums, such as the National Gallery and the Victoria and Albert Museum. And he was awarded the Royal Society of Chemistry Sir George Stokes Award for his research with ATR-FTIR spectroscopy imaging in 2015. Okay, so without further ado, please, Francesca, we look forward to your presentation.
Okay. Good afternoon to everybody. I hope you can see well the presentation. Today I'm going to show you the different application of non-invasive external reflection FTIR spectroscopy in the field of heritage science by exploiting my personal experience within the MOLAB activity. MOLAB is the acronym of a mobile laboratory, which was born in my research group in 2001. And it is composed, it was, and it is also now composed of an array of non-invasive and portable instrumentation dedicated to the in situ study of work of arts. Now, MOLAB is one of the accesses offered by the European research infrastructure for the heritage science. And we offer access to advanced analytical and scientific instrumentation, as well as access to European scientists, expert in the field of heritage science, and able to face off the different heritage research projects that can be proposed. Here you see some images of the MOLAB in action inside the museum. And the success of MOLAB is demonstrated by the fact that we traveled all around Europe, starting from 2004, where the first European project was funded, in which MOLAB was one of the transnational access. Here you can see how also the number of the available instruments increased during time. And now the MOLAB platform within the IPERION-HS project is composed, offer access to 40 advanced mobile instrumentation, and now the provider becomes 17. Among the available portable instrumentation, of course, we have external reflection FTIR spectroscopy. I look in the literature, and to the best of my knowledge, the first application of this technique in the heritage science field dates back to 1997. As a matter of fact, differently from other similar non-invasive portable technique, FTIR spectroscopy experienced a limited diffusion, at least at the beginning. This limitation is due to the fact that when we work in reflection mode, we have spectral distortion, which make difficult to interpret easier the spectra. Here you see the comparison of a transmission mode spectrum recorded from calcite in transmission mode. In magenta, you see the reflection mode spectrum recorded with a portable system. You can see that the strong, for example, the strong antisymmetric stretching of the carbonate anion appear as inverted, or better known as Australian band. By simply changing the surface morphology, we have the enhancement of additional bands that normally are not visible in transmission 1, which are the combination band. As a matter of fact, when we work in infrared external reflection spectroscopy, depending on the degree of penetration of the incident beam, we may have both surface reflection and volume reflection if the penetrating reach the inner layer. Both type of reflection generate spectral distortion. Being surface reflection generating a larger distortion like crystalline bands, as we see before for calcite, and for most of the inorganic oxyanions, like also sulfate, phosphate, and so on. When we work with organic binder, organic material in general, we have surface reflection spectra with mostly derivative-like band. The situation is quite complicated because we still have information about the chemical composition of the material, but is modulated according to the optical property and according to the two contribution of the surface reflection, which is dominating in the fingerprint region when we have strong absorption, whilst in correspondence or lower absorption band or in the near infrared region, there is the volume reflection which dominates the spectral feature with the enhancement of minor band of combination and overtone band, which are not distorted. From a theoretical point of view, we can correct this kind of spectra, obtaining profile more traditional and easier to be interpreted. As a matter of fact, when we work with material, with a surface artwork, we have both contribution to the reflectance. So this means that they are present in variable and unknown proportion. And what is our experience is better not to convert in order to avoid further distortion and obtaining misleading conclusion. In this minutes, in this webinar, I'd like to show you how it is possible, what are the information that can be achievable by working with the raw reflectance spectra. Let's starting with, for example, the pigment identification. As I showed you before, this is the comparison of a spectrum recorded from azurite in transmission and in reflection mode. The fingerprint region is characterized by distorted band due to the strong contribution of the surface reflection. But you see also the appearance of new bands, which are combination and overtone bands that are not distorted, and they become diagnostic for the identification of material, like, for example, for distinguishing the different type of carbonate-based pigment. Here you have combination and overtone band of azurite and lead white, but as cerussite and hydrocerussite, as well as malachite and calcite, as we saw before. And these can be used also for other type of inorganic compound, including phosphate, sulfate, chromate. All of them have a specific combination and overtone band that can be used for their identification. But we can work also with the Australian band. Here you see, for example, the reflectance spectra recorded on titanium white model in oil paint, in which we have different proportion of the two polymorph of titanium dioxide, anatase and rutile. And this is possible to exploit these differences also for revealing, for example, the presence of the anatase-like polymorph in a painting, in a thick white painting, along with zinc oxide on the painting by Jackson Pollock, Alchemy. Another important application of Fda spectroscopy in external reflection mode is for solving conservation science issues. I will, in a few minutes, show you the possibility of the technique for the non-invasive identification of most common degradation material, but this technique is very useful and it has a lot of advantages also for following, monitoring, and optimize restoration intervention. Unfortunately, I have not time to show you everything, so if you are interested on this part that I will not to show you, we can discuss, I can give you the literature. For what concerning the identification of metal oxalates, common degradation product that we can find both in ancient as well as modern painting, through Fda spectroscopy, we can clearly identify the nature of the different metal which is responsible, which is connected to the oxalate formation. The fact that we are working with a non-invasive technique enable also us to record in principle an infinite number of measuring points on the wall surface. This gives us the opportunity also to understand, to further improve our knowledge about occurrence, the evolution of the origin of the metal oxalate in painting. And thanks to our 20 years of activity, and we had the opportunity to investigate a lot of painting, we can say that we found the two main situations regarding the distribution of metal oxalate. We found one situation in which the oxalate patina are distributed all over the surface. And so we can correlate this presence to an origin which is linked to the addition of some material on the wall surface, like coating material or also deposition from the atmosphere. But we also found in some painting, like in this case, which is a painting by Pablo Picasso at museum, in the Antibes Museum, that, for example, zinc oxalate are localized only in one of the three types of white painting. In this case, the origin may be due to the specific intrinsic activity of each single paint, of the painting constituting material may be exposed to specific environmental conditions. But we are also very sensitive for a specific For the identification, another class of common degradation material, which are the metal carboxylate. We can distinguish the different type of metal interacting with the lipidic medium, even though the spectra appear in reflection mode and they are quite different with respect to the transmission spectra. We can recognize the different metal, the different type of carboxylate. And also the fact that we can also make a sort of macro mapping of the distribution of such degradation material, as we did for the masterpiece of Pollock, like alchemy, in which an extensive non-invasive study through Fda spectroscopy enabled us to underline the presence of zinc oxalate for the blue phthalocyanine-based pigment, for the zinc oxide and titanium white, and for the manganese purple paint. This enables also us to guide and to select representative sample for deeper investigation of such type of mechanism and degradation. This work, for example, we have carried out in collaboration with Prof. Sergey Kasarian, and maybe he will detail you better what is possible to do at a micro scale, working with FTIR for unveiling and for revealing information regarding degradation material or micro heterogeneities at a microstructure. FTIR spectroscopy in reflection mode is also very useful for decharacterization, in sometimes the identification of the organic binder. Identify the organic binder means to unveil the painting technique of an artist. And I'd like to show you the example of this type of study, reporting you some result of this wide study that we carried out on 11 paintings by Jackson Pollock, observed at the Peggy Guggenheim collection in Venice. Aim of the study was to trace the introduction of alkyd medium through FDR spectroscopy in non-invasive way in the mid-1940th century's painting. Jackson Pollock is the father of the dripping, and often the dripping has been associated with the alkyd medium and the presence of alkyd medium. And in fact, we detected the presence of the alkyd medium is his masterpiece Alchemy for dripping the black painted area. Both there was present both opaque as well as brilliant and shiny black. All of them are painted in a dripping way with the alkyd. Through FDR spectroscopy, we can differentiate different modern binder as well as more traditional binder. So exploiting this specificity, we were able to make a sort of temporal use of the alkyd painting within the painting of Pollock, correlating the compositional information with the visual appearance and information regarding the painting technique. As I told you before, we had the opportunity of investigating 11 paintings by Jackson Pollock at the Peggy Guggenheim collection. We then integrated our study with the previous published data regarding the identification also through the extractive method of the painting media on different paintings. And here we confirmed through the non-invasive study that alkyd is strongly correlated to the dripping technique. And we confirmed that the date 1947 and the day after as years in which Pollock used the alkyd medium. But we could also anticipate the use of this medium 1 year before, in 1946. Also using and not experimenting still the dripping but using a more conventional technique. And in particular, we detected the presence with the chrome orange of an alkyd medium in the painting Ice in the Heat. According also to historical record, the winter between 46 and 47 is a sort of turning point for Pollock's style. He started experimenting this data, this non-invasive data confirmed us that he started experimenting with alkyd medium before 47 with these two paintings, but then he realized that with the discovery of this medium, he had the opportunity for expressing mainly his action painting, his action art through the dipping, and so he, after the 47, he strongly, and there is the permanent appearance of the alkyd media in his painting. As a final example of another application of Fda spectroscopy for non-invasive study of object, I will show you this result coming from an MOLAB access. In this case was a national access at the Italian Trainer Design Museum in Milano, in which we had the opportunity of studying plastic historical objects. According to the literature, Fda spectroscopy as in external reflection mode, so as a non-contact, non-invasive technique, already demonstrated to be a powerful method for non-invasive identify plastic objects. In our study, we increased the knowledge by extending the explored spectral range for the plastic characterization to the near infrared, so covering the wide range from 10,000 to 400 centimeters to -1, with idea to going beyond the simple is not simple, beyond the polymer identification. In fact, we exploit the mid-infrared range, and you see here the derivative-like feature mainly following the behavior along the wave number of the real part of the refraction index, which indicate us, we can associate with this the different functional group belonging, for example, to different class of polymers, polystyrene-based polymer, and so we can distinguish when polystyrene is alone, or where it is also with a glutathione, or whether it is also with an acrylic, or where all the three are present in ABS. We can confirm, we can have further information exploring the near infrared range, in which the bands are not distorted. They are not fundamental band, but they can confirm, they can help us in the spectral interpretation of the mid-infrared range, where there is more complex, there are a lot of overlapping, so a more hard, difficult, challenging interpretation. And so, on the basis of this, we investigated a lot of objects, identifying the nature of the different plastic following both the derivative-like feature of the stronger band as well as the weaker component to the neutral component, for identifying the polymer present in the different plastic elements, for example, in this tape recorder, and also combining the mid-infrared information with that obtainable by exploring the near-infrared range. Furthermore, through FTIR, we are also able to identify the possible presence of other inorganic or organic filler or additive, as in this case, it is the tape, is still the cable and the plug of the tape recorder I showed you before. And in the case of the cable, we detected, along with PVC, present also in the plug, the presence of calcium carbonate as a filler. And you see here also from this comparison, which in both in the plug and in the cable, we still see polyvinyl chloride as the main polymer constituting the plastic. Although you see that the spectra are very different. This also allows me to show you another important point when we work in external reflection mode. It's very difficult to build up any kind of spectral database, because the same material and same sample and same compound can show different spectral profile according, as you see before, according to its morphology, also according to its optical properties that can be modified by the presence of another filler, like in this case in calcite. As I told you before, we wanted to go further, the simple identification of polymer, and so on the basis considering the fact that in the near infrared region we have generally no distorted band, and also on the basis of the wide literature in which the near infrared spectroscopy is employed for investigating plastic for other application, we also evaluated the possibility of estimate the relative content of the different monomer in polymer. In this case, by plotting the relative amount of acrylonitrile and polystyrene, just to trace and to evaluate the different polymer that compose the single element of these two grillophone and this object, the Auretta by Rosselli and Selmi, which is an air dryer. As a further information that we can give is linked to the degradation state of this plastic. I still show you some spectra recorded on this air dryer. By mid-FTIR spectroscopy, we were able to suggest that the plastic component constituting the different elements of the urethra were composed by a polymer made by polystyrene and acrylonitrile, since the absence of a butadiene as in ABS. On the contrary, by looking at the near-infrared spectra, we clearly see that in the same point, we have all the three components, meaning that we have also butadiene, and so suggesting the presence of ABS resin. We can explain this disagreement, which is not an agreement, taking into consideration the wide literature concerning the photodegradation of ABS, which affect the first layer of the material of the surface, and that this can be monitored by looking at the decreasing of the band of the butadiene component. And effectively, if we look now in the mid-infrared range to the spectra recorded on the black cap, on the top light exposed and the bottom light unexposed, we clearly see that butadiene has been disappeared in the light exposed, while is still present in the bottom. Taking consideration the different depth of sampling that we have by looking at the mid and the near infrared range, at this point we can also monitor and map the degree of oxidation of ABS, taking consideration the band in the mid-infrared range of a butadiene, which is sensitive to the degradation, to the decreasing on the first layer of the polymer, with respect to the bulk information regarding the presence of butadiene in the near infrared range. The natural evolution of this technique, this is my opinion, but I think that it is the opinion of a lot of scientists, is toward hyperspectral imaging. And I had the opportunity some years ago to collaborate with the Bruker Optic for adapting a commercial camera, generally applied for in other field for military or
1 minute. Thank you.
Yes. For other application, we modify this camera, and for the first time, with the support of single point non-invasive external reflection spectroscopy, for the first time, we were able to map the chemical composition of a small area of this painting, revealing and recording and obtaining the mixture of the complex material employed by Alberto Burri in his painting Bianco 1942. The results were amazing. I'm very happy about this study, and the strength and also the future perspective of hyperspectral imaging in the mid-infrared range is also demonstrated by further publication that then were further papers that were published after. The main limitation of all the cameras that are now, most of the cameras that are now available in the market, is the limited spectral range. In our work, the cameras was limited to this spectral range, 900/1300 centimeter to -1. And of course, it's also, according to my experience, strongly limit the analytical potentialities of FTIR spectroscopy. Thanks to a recent funding, a national funding that we have with the project SHINE, strengthening the Italian node of the ERIHS, now we are collaborating with the Bruker for developing the first camera which will work in the extended spectral range, which will cover a wide mid-infrared range going from 4,000 centimeters to -1 until about 900, 1,000 centimeters to -1. And so with this camera, I hope, but I think I'm quite convinced about this, that we will fill the gap in the present available hyperspectral imaging, which is still lacking the presence of a camera which is working in a spectral range so informative. And so we will have the possibility to exploit the sensitivity to both organic and inorganic material, the specificity on distinguishing material, as well as the robustness of FTIR spectroscopy, and so to introduce this new tool within the MOLAB offer, as well as within the heritage science available portable systems. And with this, I finished my presentation. I hope to be in time. Thanks to you for your attention.
Thank you so much, Francesca. So now we'll pass to the next presentation, which is Professor Sergey Kasarian, and then later we'll cover all the questions and answers.
Can you see my slides?
Yes.
Okay. Yeah.
Yes.
Yes. Is it okay?
Yes. Yes. Yes.
Good afternoon. I'm very impressed by presentation by Dr. Francesca Rosi. I know, of course, about some of her research as we collaborated, but it's impressively good spectroscopy and results and broad range of applications. Really very impressive. I would like to maybe talk to you about future collaboration, because I'm also a co-leader actually with Ambrose Taylor of this new network of science, engineering, research of cultural heritage. But now I will present my own research in this field. And what I would like to talk to you about how infrared spectroscopy can be combined with chemical imaging to contribute to conservation of objects of cultural heritage. So, I will talk to you about. Sorry, I put my laser pointer. Yes, it's here. So I will provide you some overview of some applications in this field, and I would like to answer your question, maybe why you would be interested in different approaches in Fda spectroscopic imaging, because the approaches what we were developing, it's quite complementary what Dr. Rosi said. And also what should be a focus of attention of conservation community. Of course, I cannot answer on my own this question, but as a community we can. And I will give you some examples of applications in my group, collaborating, of course, with practitioners in museums and at universities. And specifically, I will talk to you about micro and macro Fda spectroscopic imaging. I will focus on spatial resolution because it's important, and give you some examples how in collaboration with National Gallery, Victoria Albert Museum, British Museum, and other museums, we were able to study, for example, cross-section of paintings that provided additional information such as analysis of proteins, pigments, carboxylates. And I also will briefly talk to you about another interesting approach we developed about depth profiling with this technique, and collaboration with Perugia CITEC with Dr. Rosi. And then moving to macro Fda imaging. But what we were doing mostly in these collaborations, it's analysis of structure of oil paint, because that really has impact on cleaning and conservation of objects of cultural heritage. So I just would like to introduce briefly Fda spectroscopic imaging. If you shine light onto the sample and collect on array detector, and array detectors typically are 64 by 64 or 128 by 128, each pixel would measure a full infrared spectrum. And if you plot absorbance of the band, you can create a chemical map corresponding to particular chemical group, for example, or chemical substance as well. So if you select another band and plot absorbance distribution here as a function of all pixels, you can see that the image is quite complementary, two main components. Of course, we can create in single measurement chemical maps for all components present in the sum. And I would like to remind you that all the spectral bands depend on vibration, it comes from vibrations of molecules. It's important to realize that, of course, these vibrations exist because sometimes, even in books, phrases used that infrared radiation causes chemical bonds to vibrate. Well, if they were not vibrating in the first place, such interaction would not occur with infrared light. But this analysis, of course, we call univariate analysis. And of course, this image really worth 1,000 spectra. And sometimes we use also multivariate analysis, chemometrics, when it's really necessary. So in infrared spectroscopy, we have different approaches. Transmission, you can see here, sample thickness would be limited to 5 or 20 micrometers. External reflection, and that's what Dr. Rosi mostly was talking about, and provided actually very high quality results. And ATR, I will be talking mostly about this ATR combined with, and I will explain to you what ATR is, combined with microscope, infrared microscope. In this case, thickness is not really limited, well, within the reason. So here I show principle of ATR approach. It's internal reflection, not external. You have a crystal with high refractive index, typically like zinc selenide or diamond. You place sample on the top, and when certain conditions are met, and I show you here what conditions are met, this animation on the right-hand side, you can see I increase angle, incident angle, and only when I reach critical angle, which defined by Snell's law, internal reflection occurs. And when it happens, electric field of light still would penetrate into the sample, but as an evanescent wave. It would be decaying exponentially, and when it decays by factor of E, it's called depth of penetration. Of course, probing depth is greater, but it allows you to measure samples relatively easy if you get good contact of up to several micrometer layer within this sample. So here, one of our older system, but I show you we have infrared spectrometer and two accessories, infrared microscope for micro studies where spatial resolution reaches 2 micrometer, and macro where we don't use microscope, infrared light bypass here microscope, and if you have inverted prism, you can study bigger areas. So here I provide just some idea of what kind of field of view or areas we can measure in single measurement. Here you can see millimeter squares, but it comes at the expense of spatial resolution, for example. Here in Diamond ATR, which jointly with Spectra company, we developed this approach, gives quite a good spatial resolution, but its micro ATR imaging, this microscope really provides highest spatial resolution. And we were built some accessories with expanded field of view, or as I said, this spectroscopic product from SPECAC, where focusing lenses help us. This slide is quite complex, and I would like just to point out that spatial resolution, of course, defined by Rayleigh criteria, wavelength of light divided by numerical aperture, and numerical aperture determined by angle here, this angle, half of this angle, and refractive index. So if you take germanium crystal, here the media where infrared light passes, refractive index 4, so you increase numerical aperture by 4 times, and therefore we increase, well, we can resolve much smaller features. For example, here, stringent test, we introduce measuring interface between 2 different polymers, and then we measure how absorbance decays as a function of pixels here. You can see it's about 4 micrometers. It's important to highlight here that we were using 64 by 64 pixel. And if we divide this area 50 micrometer by 50 micrometer, 50 by 64, actually spectra different within less than micrometer. But strictly, spatial resolution would be 4 micrometer for this wavelength in fingerprint region. And this slide basically re-enhances the same idea, provides you some opportunity of articles where we reviewed issue of spatial resolution in great detail, because spatial resolution very often still used as a pixel size. Of course, pixel size is not spatial resolution. So one more point about chemical imaging with array detectors, with infrared array detectors. If you use a single element detector on infrared spectrometer, your information would be average. And if some particle present here, it's usually would be overwhelmed by spectral information from all the samples. So it's average. With array detector situation, and I have done here such experiments, diluting powder of 2 different components further and further. And you can see we can detect almost pure spectrum, because from these locations, we can obtain pure spectrum of this particle. And we use it in forensic very much. For example, here particles trapped. With single element detector, it would not be possible at all. And my collaboration with National Gallery started when Marika Spring and Catherine Higgett, who gave a wonderful talk with Professor Dragotti from Imperial College a few days ago. So they visited and asked about possibility of collaboration. So one of the first examples of what we collaborated there was a painting of 15th century. And the idea was that in National Gallery, microscopic samples like cross sections have been already extracted and embedded. So samples were available, but resolving a very thin layer of very small particles was a challenge. And yes, so here I would like also to mention Camilla Ricci, because at that time, when colleagues from National Gallery approached me, she was in my group on forensic project, and she came from Perugia. And so she also helped me, facilitated our interaction. So the sample has been extracted from this part of the painting by Sassetta, and particularly to analyze this translucent areas or regions in the sample. And you can see by visible microscope, there are different layers. And of course, these microscopic samples have been embedded in epoxy in order to handle it under microscope. So, and that's really interesting results, because you can see now chemical images based on distribution of spectral bands. And here we have got resin, of course. It's not much of interest, but exciting part came here. This layer number, because I want to remove this window. Okay, that's better. Yes, at the bottom. Okay, on my screen, I'm doing some adjustment. So let's start from this one. Distribution of amide band revealed that there are actually protein is present, obviously as a binding media. It came from egg and created egg tempera here. But distribution of lead carbonate, which was used as a pigment, was present here. And then what was most exciting, additional substance was found here, lead carboxylate. And this was really exciting, because I would not show here spectra, because lead carboxylate in such type of samples has not been detected before, because as you can see, it was very small amount in very thin layer. Another example was a painting of from Florentine school, where we were able to detect here particles of malachite. Malachite, if you compare a reference material, you can see some bands overlap. But between or here, you can see, we were able to detect again egg product containing proteins via amide bands. Of course, here amide bands may be not entirely clear because it's overlap with one of the antisymmetric vibration of carbonate of malachite, but assignment was unambiguous here that we were able to see binding media as well. And this might be a slightly better view. You can see, for example, these particles, very small particles, maybe few micrometer. They were confirmed, of course, by scanning electron microscopy. But organic materials have been detected by these infrared studies. And importantly, we were able to detect something else apart from malachite and protein, and it was copper carboxylate. So it's again, this is type of materials that sometimes disrupt painting carboxylates called metal soaps. And we were detected by unambiguously by presence of this spectral band. It's just one slide on another example, because we collaborated with Royal College of Art at the same time, some years ago now, when we studied albumin photographic prints. And this layer here, it's a very thin layer, about a few micrometer. It was showing, again, product of albumin, and that's what's important. And I don't unfortunately have time to detail of this study. But my current student, Guan Lin, he now studying other albumin photographs of end of 19th century, beginning of 20th, and their degradation. So very quickly, because I was quite ambitious with my slides, but I would like to show you a new approach of what we have developed a few years ago. So we decided to introduce aperture in microscope objective. And that's not standard aperture that usually would define area what you image. It's actually aperture that changes angle of incidence. And if angle of incidence change, you can select small angles you have seen on previous slides, or large angle, and depth of penetration would be varied. So for example, in previous presentation, photodegradation samples might benefit from such type of approach, because in depth of penetration equation definition, angle of incidence present here. And so we were able to measure layers of different thickness by changing angle of incidence, and of course, obtaining information in 2D. But here, diffraction limit is not applicable in that direction because of the evanescence wave, and you can resolve really small steps, 100 nanometers. For example, Alexander Vicky, who was doing PhD with me recently, she finished now. We collaborated with the Victoria Albert Museum. I would like to go very quickly through these slides, because here it shows some plaster materials. As you know, there are some objects in Victoria Albert Museum. Usually they're coated by skin glue for protection. And here we were able to see, yes, we can see beyond 2 micrometer to see the gypsum. And here, using different aperture, we were able to obtain different spectra and probe deeper. For example, here, it's particularly striking that this, for example, bands much more visible with using specific aperture to measure such type of samples. So, and Francesca Rosi already mentioned about painting by Jackson Pollock. But here, I would like to show you our results in collaboration with their group. So what we wanted to study by ATR FDR microimaging, how fatty acids interact with salt binder and basically form metal soaps. As you know, oil can interact with some oxide, for example, metal oxide, saponification reaction. But important that it would be very destructive formation of soaps of carboxylate, disruptive for painting. And in this case, I just would like to show you results of samples removed from real painting, but it actually was from some small droplets on the frame of alchemy. And what was remarkable that apart from of course zinc oxide converting to zinc soap carboxylate, we were able to see that it happens around aluminum stearate, which was also added to the painting at that time. And this basically shed the light why this painting was fastly degrading. And group in Perugia provided, and also student came actually here to Imperial College, model samples. And model samples were artificially aged by higher temperature or humidity. And these results, having carboxylate of zinc and aluminum stearate position very close to this substances, was also found in model samples. I think my time may be soon finishing. I would like just to show you very recent work. It's a different collaboration with Milan. In this case, you can see several layers we were studying, and particularly this layer was very important. That was from objects of cultural heritage in Italy. And I collaborated with Elena Passetti, again, to detect soaps, in this case times a formation of lead soaps. I would like to show you some spectroscopic systems in my lab. And you can see microscopes are present here, but we also have system without microscope to study macro imaging using inverted prism. So for example, in this collaboration at that time, almost 10 years ago, another Italian collaboration with a group in Milan, you can see samples, leather, polychrome sculpture, and terracotta piece. These samples are not so easy to measure with micro ATR crystal, but using this Golden Gate accessory, especially resolution 1015, again, it's based on our development, we were able to measure these samples. And you can see, for example, in most of them, we were able to identify and resolve chemical composition of each layer. But the challenge was here following, because these samples, of course, we can slightly press, not much, because you can break some very easily. And when surface is rough, it shows a limitation of ATR approach. However, here we added a droplet of water. It was possible with these samples. And we basically created immersion liquid. And we were able to obtain good spectra and images, and water was not interfering using this approach. I also would like to show you one just results. It was recent collaboration with Institute of Ancient Manuscripts in Armenia. It's one of the largest depository in the world of, and particularly for Armenian manuscripts, of course. And there was degradation of ancient manuscripts because of leather. And we were able to detect in these samples also formation of calcium stearates. And if you would like to read about this, you can read this article. One of the maybe last slides that I have, it was a collaboration with Satoko Tanimoto when she came from British Museum working in my group. Remarkable again, this type of samples from bronze statue was possible to measure on diamond, and we were able to differentiate all type of copper pigments, but that's not published, unfortunately, yet. So I would like to finish my talk to saying that micro ATR and macro ATR, of course, I didn't discuss much optical distortions like Dr. Francesca Rosi did. Very useful for studies of objects of cultural heritage, and macro imaging, particularly for objects like sculptures, parchments, wall paintings, and plastics as well. Of course, as a modern approach here, we use different techniques. And but spectroscopic imaging is a main focus of our studies. There are many issues maybe still to be addressed, but I would like maybe to thank my collaborators listed here. It's not even all collaborators who really shared their practical expertise in this field, and I'm happy to assist them in the efforts for preservation of objects of cultural heritage for future generation. Thank you very much.
Thank you so much, Sergey. So let me switch on my video. Yeah. So I have a, yeah, so let's open the opportunity for questions for both. So I'll start with Francesca. So I wonder how much can you, with your techniques, how much can you penetrate in the paintings?
It's a quite difficult question. It depends on the material that are above. When we work, when we explore the near infrared range, working with in painting, for example, we normally see the gypsum preparation. So we can go from, we can see the, so I don't know exactly what is the thickness, but also in presence, for example, of lead white, which is one of the common white pigment also for the imprimitura, and this is also a quite stronger infrared absorbing material, which could block in part. We normally see also gypsum. The lucky things is that, of course, one of the main limitations of non-invasive technique in general, especially FTIR, is that we are not able to give information about the stratigraphy, but we can inform something about, because exploring the wide, for this, I think that is very important to use the most extended range, because looking in the mid-infrared, I'm mainly sensitive to the surface. And then I can exploit the higher penetration in the near infrared. I can give you the thickness, but I can give you if the material is over or behind.
Mm-hmm. Okay, yeah, thank you. But I guess it will be in the range of micrometers, no?
Yeah, the range of
mm-hmm. Yeah. And Sergey, I know you have been also working a lot with Raman. Yeah, could you please comment on how you've also incorporated Raman and combined it with the infrared spectroscopy?
Well, that's true, Salvador. We use Raman a lot, but not in this field, surprisingly. No, but we, for example, studied polymeric fibers and polymeric materials. And there, for example, in terms of confocal Raman can be used for at least 150, 250 micrometer depth. But they not so surprisingly, resolution would not be so good like our approach with changing angle of incidence, where we can go by steps 200 nanometer, for example. But of course, only within few nanometer. So Raman complementary in many ways. And for example, one group in the United States, in collaboration with the Art Institute of Chicago, they applied tip-enhanced Raman, which we're also using, but for different applications. And tip-enhanced Raman was able to differentiate some inks because it's has potential for detection of single molecule. But of course, challenges different. Each technique has challenges. I know that Professor Robin Clark at UCL, he not any longer with us, but he did a lot of research using Raman for studying pigments in different paintings, and his former PhD student, Lucia Perugia, she now works at Victoria Albert Museum.
Mm-hmm. Great. Do you have any questions among yourselves?
Well, that's very interesting.
Yes, I have.
Yeah.
I have. Can I start? I have two. One is not a question; it's just something which is very interesting: the changing of the angle for probing different depths. So this is one of, I think, that's a good perspective also in the field of cultural heritage, the possibility of investigating at the chemical level the subsurface. And so this is very interesting. The other question was more practical, but and it is more useful for other my experiment. But when you said that you applied for the macro ATR in order to achieve a good contact, you just added some drop of water. And how water is not interfering in your spectra? In what way? Because we recorded the spectrum with water and then you subtract?
Yes. No. Basically, of course, if there are some substance that would be dissolved, for example, or react with water, that's of course not good. But those samples were very robust. I mean, for example, we can, of course, we're measuring some part of the sample. And before water or after water, they did not change. Of course, it's not applicable to all samples. And of course, it's possible to use not necessarily water. If you know that it would interact with water, we can use carbon tetrachloride, for example, or some other immersion liquids. But the key was, if you have air, gap, quite big air gap, let's say 2-3 micrometer, then we cannot actually see sample in this area, which is above, And when you added water, it's like matching refractive index to sample. So a light light goes deeper. So that was the idea. And it's worked really remarkably well. It was described in this paper, vibrational spectroscopy. It's not applicable for every samples, and but this is a way to deal with rough surfaces. Because if you press, of course, sometimes it might work, but sometimes not. And but however, for example, like parchment or leather, there we also can assess whatever contact good or not by using polarized light. There are some theory developed quite simple. If you measure spectra in 2 different polarization at 45 degrees incidence, it should be a ratio of absorbance should be 2 between this. If it's if contact is good, it would give you up to 10 nanometer precision that there are no air gaps. And we have published it in different research. We published when we studied skin to under control humidity, for example, and different samples. We applied this approach. We apply this approach to assess how you achieve good contact. Yeah, so yeah, that's my answer. So because of course there are always challenges, but there are always ways to find solution.
Do you have any questions, Sergey, for Francesca?
Yes, I was overwhelmed by how much research you have done. I was, in fact, I'm very much impressed, and particularly with plastics, modern plastics, because we at Imperial, we also have plastics in air, plastics in ocean, but degradation. So photo degradation, when you studied butadiene, maybe it could benefit from some of our approaches. Maybe we should discuss and would find something very interesting together.
Yeah, it's a good idea. The lucky thing is that I'm usually to see spectra from CIR reflectance spectra from painting, especially old painting, are sometimes very noisy. The good thing is that when we record the spectra, the main problem on plastic is not to have a good spectrum, but to interpret, because they give very nice spectra. So there is a lot of space for working on them because they are very good. So it is, but
yes.
we can keep in contact on this because
Yes,
I have in
yes,
mind
indeed.
some project on plastic, so we can.
Yes, no, that would be very good indeed. Because, as I said, I was impressed that you needed to deal with all these aberrations and distortions with spectra, because external reflection, it's quite challenging. Very challenging. Well, I have seen a number on your slides that I thought, well, not that I can ask you to act as a reviewer. You're one of the best reviewers for applied spectroscopy in this field. You know that. No, really. But also, I would encourage you to submit more papers to applied spectroscopy. I don't know if you have seen, for example, well, sorry, it would not appear maybe because of my background. You know, oh, I'm disappearing.
Yeah, we see it.
It
Okay,
disappears.
Cava, yes, it's also a school of Leonardo. It was much issue. It's another Italian group published an article in applied spectroscopy. So I just would like you to welcome.
Okay, I will do. I will take it as a.
Okay. Okay, thank you so much both. So I'm gonna close the meeting because we are already overrunning. So thank you very much, Dr. Francesca Rosi and Professor Sergey Kasarian, for your amazing presentations. A recording of this webinar will be in the YouTube channel of the IMSE. You can find the links in the website or here in the chat. And the next webinar in this series will be a highlight webinar on 22nd of June at 2 p.m. on the theme of laser and optical technologies in heritage science. How smart can we get? And we will be presented by Professor Demetrios Anglos from University of Crete and also an associated researcher at IESL 4. Okay, so thank you so much, and thanks to you. Yeah.
Thank you, Salvador, and Francesca. Thank you. Bye-bye.
Thank you for the invitation, Sergey. Ciao.